Alright, so hi, my name is Mary Plauche, and my research from this summer is going over achieving energy efficiency via heat recovery from building scale water recycling systems. So I first wanted to bring back this diagram that I've shown before. This shows the energy-water nexus, how energy and water relate. So if you look on the left side, you can see the separation between energy and water, but as you move over to the right, you can see how they are integrated, that they're related, and more we're realizing in our research that we need to understand this relationship between energy and water, and you can't really make decisions anymore without considering the two together. So for my research, I'm looking at the relationship between energy and water in terms of wastewater. So we're trying to understand the energy use involved with applying wastewater reuse within a building with either graywater, which is like non-sewage water from your showers or sinks, or wastewater, which is everything in your house. And we're particularly also looking to see if we can recover heat from this wastewater, since it's at a higher temperature, to reuse for preheating fresh water. Okay, so in order to create this model, we had to acquire quite a bit of data. So first we need to find temperatures of water supply and wastewater. So like what the temperatures are of different gray water after they're used, or like the temperature, typical temperatures of wastewater. We also need to look at the energy involved with the different treatment methods. So there's a lot of different methods for treating gray water, and to see how much the energy would take per amount of water to do that, as well as with wastewater, and to also compare this to what it would take to treat and supply fresh water, like normally within a community, as well as collecting and treating wastewater. We also need to look at the end uses of water within a building. So how much water is going to end up being used in showers or toilets, and how much of this is hot water, stuff like that. And what's also for the heat exchangers, we need to know the values for the surface area and overall heat transfer coefficient, which I'll get to later. So for our study system, we looked at multi-residential buildings at the scale of having 100 or 200 units per building or set of buildings. We also assume that there's 2.5 people per unit, and that each person uses about 58.6 gallons per day. And also that we consider that this use number was consistent even with the efforts to reuse. So we weren't thinking that people were suddenly going to take more showers just because they knew they could, because the water was being reused. So just to be consistent. Okay, and there's a couple different energies associated with water supply and wastewater treatment. Usually if you have a larger facility, it takes less energy because there's an economy of scale. You can treat more water with you can just treat more water. So we have a range of values. And we did this because we wanted to look at Denver wastewater, which treats about 130 million gallons per day, and they can do this really efficiently. But Denver is one of very few of these really large facilities in the United States, so we also wanted to look at a more typical wastewater treatment facility, which treats fewer gallons per day and also requires a higher amount of energy. So some more assumptions. With our gray water, we assumed that the treatment method was for sand filtration and UV disinfection. And there's also, we had a range of estimations for how much energy this would take to do. We weren't so sure, so we had a low and high energy estimations between 3.4 and 8 kilowatt hours per 1,000 gallons, which I'll show in my graphs. And For wastewater, we assumed a small membrane bioreactor for the treatment of all the wastewater. And also, we only considered the amount of energy it would take to treat and reuse for toilet water, which in a facility is about 7,000 gallons per day. So in our 200 unit complex, I divide this between the smaller wastewater treatment plant, which takes more energy, and the larger wastewater treatment plant, which takes less energy. So on the x-axis, I have conventional and then graywater reuse and wastewater. Conventional is just not applying, reusing any of the water. So it's just the blue shows the energy to supply the fresh water, the red for wastewater treatment, the green is for on-site reuse energy, and the black dot shows the volume of reuse. So since this is just taking everything from the water supply and treating everything through wastewater treatment plant, there's no energy to reuse because you're not reusing, and so there's no volume. So it's pretty, for the low energy, for the gray water, it's a little less to reuse on site. The wastewater is definitely a lot higher, as you can see, even with the larger wastewater treatment plants. We can also see similar results with the 100 unit complex. It uses a little less energy overall to supply because there's less water demand in this type of building. But it's still better to, it looks like at the low end for gray water is the best way to, it's a little more energy efficient. So if you're more concerned with needing to save water than how much energy you're using, this might be a good option to treat your gray water. So for the heat recovery aspect, we use a series of 3 equations. The first one relates, Q is heat, m dot is flow, C sub P is the heat capacity of water, and then the difference is in temperature. So we knew the changes in temperature of our wastewater, and we used that and the flow rate and the heat capacity to find the total heat availability. And then we took that and applied that to the incoming fresh water to find the final temperature of fresh water that could be transferred, the heat that could be transferred from the wastewater. And so we needed the 4 temperatures, the initial and final wastewater and the initial and final freshwater temperatures to find the log mean temperature difference, which basically is a measurement showing the temperature changes on each end of the heat exchanger. And we need this to find the total heat that can be recovered, which is Q again. And also, so applying the log mean temperature difference, the surface area of the heat exchanger, and the U, which is the heat transfer coefficients. And those are, I used standard values for, I assumed a shell and tube heat exchanger, and we just used standard values from that to do my calculations. So for our heat recovery scenario, I assumed, I used the scenario of the 100 unit complex with a smaller wastewater treatment plant. So on these bars right here, this is the total energy for no heat recovery, showing the gray water, the energy to treat gray water with a low energy and high energy estimation, as well as the wastewater. And then this shows the energy it would take if you recover gray water from an individual unit and applied heat recovery. So you can see there's a decrease from the overall gray water use. Similarly with the building, there's also a decrease. There's also, if you apply heat recovery to wastewater, you can also get a decrease in total overall energy use, but it's still not good enough compared to your conventional system, which you can see with the red line. It's still more energy efficient. So In summary, we said that the total energy used for graywater reuse systems can be comparable to conventional water supply, which you could see, especially with the low estimation, that they're pretty close at least. But the wastewater treatment requires more energy, so it's not as feasible as it would just to keep the conventional water system. That on-site graywater wastewater is more energy efficient in scenarios where wastewater treatment plants require more energy for treatment. So the smaller, if you have a smaller wastewater treatment plant that requires more energy, it could be more energy efficient if you reuse graywater instead. And then the addition of heat recovery has the potential to reduce energy consumption below that of the conventional water supply. And that's what I got.